Assalamu alaikum wa rahmatullah. Today, experiment we have is lumped capacity model. We use this model to simplify the heat transfer problems related to unsteady heat transfer. So if I have a system unsteady, okay, heat transfer, so the system is, suppose that we have a body and this body is supposed to sudden change in the temperature and the surrounding temperature. So that is there is temperature is a factor of two things, factor of time and factor of position. So x and position. So to model this problem it will be difficult because I have two significant factors affecting on the temperature, time and x. So this model used to simplify the temperature, supposing that only the temperature is factor of time and the x or the position has no contribution to the system. So we can say lumped is a model to simplify the unsteady heat transfer problems. And we, in order to assume this, we just assume that the temperature inside the body itself, there's no resistance for the heat transfer. So there is no, so only the heat transfer is only in the surrounding. So now temperature variation within the mass of well-conducting solid or well-mixed fluid can be neglected. So no resistance. So heat just come inside. All points should be almost the same compared to the outside temperature. That means, again, so the resistance to conductivity or the conductive heat transfer is negligible to the resistance to the convection heat transfer. Okay. So if we apply this model, then we can easily have this equation: ln temperature at certain time minus T infinity, so it's the temperature of the surrounding, divided by T initial, so it's the initial of initial time, minus temperature infinity. It will equal to minus HA. H is the heat transfer coefficient times A, surface area of heat transfer, overall rho, density of the solid, volume V, volume of the solid, Cp, specific heat transfer of the solid, time. So we can just apply this model directly without need to calculate the x, the position. But in order to have this model valid, we should have Biot number less or at least equal 0.1 or less. So what is the Biot number? Biot number is the resistance to conductivity, overall resistance to heat transfer coefficient. So that means H over, if we rearrange it, HLC over K. So what's LC? It's the characteristic length. Characteristic length. So characteristic length here in the body is volume of the body divided by area, surface area of the body. Okay. So for if it's sphere, so it will be R over 3. Radius over 3. Cylinder, it will be R over 2. For cube, it will be L over 6. So how do we get this model? So now, if we suppose that we have this body of object and it has a certain temperature, has a certain area, density, mass and volume, and then suddenly it put in a surrounding that have T infinity. Now let's assume that the heat transfer is, the change in the internal energy will be only due to the heat transfer. So we can say H A T minus T infinity will be equal to minus M Cp delta T over delta time, temperature and time. So this is the change in the internal energy. So then M, the mass is equal rho V, density times volume. So we can say HA times T minus T infinity equal minus rho V Cp delta T over delta time. So we can, in order to integrate this equation, we will take the temperature to the left side and keep, or we can take the time to the left side and move this other part here. So it will be delta temperature, delta T over T minus T infinity equal minus HA rho VCP delta time. By integration, so this is from time initial to time, and here from 0 to time, so we can get ln T minus T infinity over T initial minus T infinity equal minus HA rho VCP time. So now this equation is the same equation we got here. Okay. Now, but in this equation we ignored the effect of conduction. We assumed also the temperature heat transfer, it's all, the internal is only due to the convection, and we neglect the effect of conduction. So now let's introduce the conduction in this equation, but in the way to keep the balance of the equation. So I can time this equation times K over L, this is resistance, this is conduction, K over L, because as you know the conductance K delta X. So it will be K over L, L is the characteristic length, overall K LC again. Okay, so it will be 1. So if we add it here, it will not affect the balance of the equation. Of course, A over volume, it will be equal to 1 over LC, characteristic length. So now the equation, if we multiplied K over L overall K over L, so we can make it H times L. Okay, we said this one will be K over L times L over K. So let's take H and L, okay, and over K over K. So it will be HL over K times, take the other part, K over L times this part, so it will be K over rho Cp, and LC we have L, so it will be LC squared. We have two squared characteristic lengths times T. Okay. As you know, this one is a Biot number. This one is alpha, thermal diffusivity. Okay. And this squared characteristic length. So this equation can be written as Biot number times alpha over LC squared times T. And from heat transfer definition, L alpha over LC squared times T equal to forward number. So this is forward number. Now, so this can we say this is the overall unsteady heat transfer. So ln the left side, ln T minus T infinity over T initial minus T infinity against forward number, we should get a slope that's equal to Biot number. So in the experiment, we have a shape, any shape, but in our experiment, our shape will be sphere. Okay, sphere, and it's connected like this. And we suddenly put it in a pass water that has T infinity. So we know the initial, and we know the T infinity. And in the experiment, temperature will be recorded against time. So we have T, let's take another color, time and temperature. Okay, until it reaches equilibrium. So for example, for a cooling, it will be like this. and for heating it will be like this. Okay, so we can find the T initial, we can find the T infinity, we can find T with time. And when we plot len T minus T infinity over Ti minus T infinity, again it's forward number. Forward number is the properties of the shape. So for sphere you can find the rho, you can find the C, Cp and C, all these properties for the shape itself. Okay, times time. So we can find the Biot number. If Biot number is larger 0.5 or less, then we can apply lump capacity model to this shape. And then we can use this equation. Suppose that I found the Biot number is 0.1. Then my case, my shape is lumped model. So it's applicable to lumped model. So since it's applicable to my model and I have the Biot number here, so we can say now Biot number equal, we said H LC over K. So since I get this value from the slope, okay, and LC is known because it's the characteristic length volume over area, and K is the conductivity of the shape itself, so I can find H. Once you get H, then you can apply it here, okay, to calculate the time at different temperature. So now you have, this is the real data, real experiment data, then you can apply your own model based on lumped H, calculated H. So this will be the theoretical model. Okay, so this is experimental data, and this is model. Okay, it should be almost when H almost less than 0.1 and less, so almost 2 points will be very close to each other. If you found it not model larger, so you will find the difference between them. You find the difference because now there's no more lump model. It has significant effect for the conductance. So there's a resistance inside. So we will apply the experiment 2 times, one for heating and one for cooling. For heating, we will take the sphere at room temperature and put it in hot water and check the time and temperature sensors. And then we will do the reverse experiment. So the opposite way, we just take the sphere from the water and just put it in ice tank and then find the way of cooling. So this is all about experiment, and now we'll go to how to see the equipment itself and how to do the experiment actually. So we have this shape. This shape is a sphere, and we want to test if this shape is lumped or not. So it's applicable to lump capacity model or not. So already this shape has a room temperature currently, and then we will put it in this bath water. So this bath water has a temperature around 55 Celsius degree. And once we put it, we will measure the change in temperature per time. So then this will be the first experiment until we got steady state. So no more increase, almost the shape reach the surrounding temperature. So it will be my first experiment. And then we'll repeat the experiment again, but in case of cooling. So just we'll take it out of the bath water and put it here in ice box. This ice box, we have temperature to ensure that the temperature is correct. Then we will measure again the change in temperature for cooling, and then we can check the Biot number, and if the Biot number is 0.1 or less, then we can apply the model, lumped model. So now let's see the setting here. Now we have the initial shape. The shape surface temperature is 16.2. This is the temperature of the lab, and we also have, this is the bath water temperature is 55.9 Celsius temperature. We also have shape cone temperature or datum. So this is like a reference. Okay, the shape, the temperature inside. This is from outside. So and here also we have we can make for the configuration of the sample. I can measure the sample intervals continuously every 10 seconds or less if you want, but 10 seconds is fine. And continuous. Okay, we can set the temperature from here, increase or decrease the temperature. So now we can start the experiment. So now let's go for the Excel sheet. Okay, so once I put the shape in the liquid, in the water, hot water, so I should in the same way press go. So go to take the initial, go. Now. So now the shape was 15.7, okay. The pass water is 55. Then as you can see, the temperature of the shape increased. So it increased every 10 seconds. It will increase. Now it's become 23. Then 29, and so on. It will continue increasing. So here we should have a curve, but it's not represented yet. Okay, so let's go back again for Excel. Now 41. So it's almost very close. And as you know, for heat transfer, we start by a huge driving force between the initial and the infinity, T infinity, and when the temperature becomes very close, the driving force will decrease, so it will take some larger time or longer time, so the curve will be parabolic. Now, as you can see, the driving force become less, okay. So if you take, for example, the difference here from 16 to 23, it was huge. Difference huge. Then here the difference become less because the driving force become less here as we reach almost to the temperature. So 49. Temperature almost become very close. So here we have the elapsed time. So this is every 10 seconds. And here we have the pass. So the most important temperature you should calculate is the temperature of the pass water. You can consider it constant, or you can take the real data. And here the shape temperature. Once the temperature become almost constant, so the driving force is very small, so you can then save the data, save as, okay, and save the data as Excel. Okay, Excel. And this run will be heating, so should be make it heating. You can put the date and the file name. Okay. Now, so we can consider it almost finished. So we can make stop, okay, and then we can create new, okay, file to do another experiment. So now, take it out. So the initial temperature. We can put it, once we put it in the ice box, we press go. So now, of course, don't take the pass temperature because the pass temperature is a sensor for this. That's why I put a thermometer here to measure the actual temperature. So it's 0. So the temperature here is 0. Now, what you will take only the shape temperature. So it starts at 53 towards the chip temperature, then it decreases. Now it decreases until the same way, until it reaches almost 1 or 0. It will take maybe longer time than heating. So maybe 5 or 6 minutes. So until it almost becomes 1 or something like this. So, and then you can take the data and plot it to calculate the Biot number, to find the Biot number, and find the if this shape is lumped or not lumped. So this is the experiment. I think it's easy, straightforward, and you can do all your calculation also straightforward. Thank you so much.